This lesson focuses on finding possible rational zeros using the rational root theorem test. All right, here's the definition of the rational root theorem. What this helps us to do is to find the possible rational zeros of a function. These are just the possibilities of some zeros, some real zeros. In order to do this, the possibilities, we take the factors of the constant term divided by the factors of the leading coefficient. So I have an example below here. So what we're giving you is a function. The degree is 4, so we could have up to a possibility of 4 real roots, or zeros, rational zeros. This is called a quartic function. So we're going to pick apart two important things. We're going to take the leading coefficient, which is 1, so that's found right here, and the constant. Don't worry about the negative. Those are the two numbers we're going to work with to use our rational root theorem. So what you do is you take the factors of the constant, so 6, think about factors of 6. They are 6 times 1, 3 times 2, so the possibilities are plus or minus 6, plus or minus 3, plus or minus 2, plus or minus 1. And then we take the factors of 1. The only factors of 1 are 1 times 1 and negative 1 times negative 1. So what we do is we divide these. We take plus or minus 6 over 1, plus or minus 3 over 1, plus or minus 2 over 1, plus or minus 1 over 1. And we get a total of 8 possible real roots, called rational roots, because we could end up having some fractions, but in this example we don't. So these are just some nice integers. In order for us to prove that any of these above roots are in our function as x-intercepts, let's say, I do have a screenshot of a function typed into my graphing calculator. There's the function, and if we look at the function's graph, there is a x-intercept right here and another one right there. And I do have a picture also of those data points. That 0, negative 6 is right here. And then I have, just going to erase that because it got a little bit too thick there. Then there's some more points here. I have an x-intercept at 2, 0. So this is 2, 0. So what we could do is we could start off using synthetic division with x equaling 2 and synthetically divide it out and see if it works out. Now, I'm going to go ahead and just show you an example. You do not need to write this down. Just kind of listen and watch. So find all the rational zeros of a function like this. So this function is not in standard form. So first we do is we take and write it in standard form. Then we take the constant terms, 9, and we factor it. And then we take the leading coefficient, which is 2, and factor those. So here are all...
Mr. John Stoll, please dial 3702.
All right. So then we would list all the possibilities. And then we could take a graphing calculator. Notice that we could have up to 4 possible zeros. Now what we did on this slide is we just started choosing some random numbers. So let's start off with 1. We'll use synthetic division. Notice that there's a remainder. It's not 0. So we know that we will not have a root at x equals 1. So no x-intercept. Then let's try negative 1. Use synthetic division. Notice here, we get a remainder of 0. So this is going to give me an x-intercept. Again, you don't have to write this down. You're just watching. Then we just choose another one within our list from the rational root. And we get another remainder of 0. So here's another x-intercept. And then you would just continue so on and so on. Here's one more. So we'd have another x-intercept at x equals 3. In order to prove it, we use synthetic division. You could use long division, but most students tend to not like that. So this is just finding the possibilities and then testing them. We will go into another example in more in depth.